Hello everyone, my name is Jatin and today we are going to discuss about various types of filters and their performances. The link to this repo can be found in the description below. So let's start. We are going to discuss about three types of filters: the moving average filter, the first order difference filter, and the 3-point central difference filter. The detailed lab sheet can be found in the link given here, and as well as various MATLAB codes written for generating pole and zero plots can be found in the link. So the first filter we are going to discuss is the moving average filter. The moving average filter is a simple low-pass finite impulse response filter. It takes some samples of the input, finds the average, and produces as the single output. The time domain equation of the moving average filter is given here, and the Z transform of the time domain equation is this. The transfer function can be easily found out by finding out the ratio of yz to the xz. Now if we take 8 samples to find the average, that is the L equal to 7, the transfer function looks like this. Now we can find the poles and zeros of the transfer functions as well. As we know that the zeros are those values of z where the transfer function attains zero value, and poles are those values of z where the transfer function attains infinite value. As you can see here, there are 7 zeros as well as 7 poles, given that all the poles are situated on the origin, and the magnitude and the phase equation can also be found out using the transfer function equation. Here, we can also plot the magnitude and the phase response of the transfer function. This is the frequency axis, this is the magnitude axis, as well as this is the frequency and this is the phase axis. We can find, on analyzing the magnitude plot, we can see that the plot looks like a comb, and this is the poles and zero plot. All the 7 poles are at the origin, and there are 7 zeros which are situated on this circle. Now let's take a look at the code. We have the input data which has 1000 samples in it. You can find the data file here. So the void setup is used to initialize the conditions. Here we are setting up the baud rate as 9600, and while loop is used to run the code written in it repeatedly for infinite times. We are initializing the array to store the moving average when giving all its elements the value 0. The window size we are getting is 8 samples, and this for loop calculates the average of the 8 samples taken at a time, and this line is used to print the input and the output of the filter. As you can see here, when we take the window size of 8 samples, the blue plot is the input plot and the red plot is the output plot. The blue plot and the red plot, the difference between both of them is that after the output of the moving average filter is more smooth than the input. And when we increase the window size, what we see is the baseline of the signal. When we increase the window size, the moving average filter becomes a low pass filter and only allows the baseline to pass from the filter. Now, the second type of filter we are going to study is the first order difference filter. The first order difference filter is a finite impulse response filter where the previous input is subtracted from the current input to get the current output. As we can see in the time domain equation, the previous input is subtracted from the current input. This is also known as a derivative filter because it essentially emphasizes the high slope components of the signal. So this is the Z transform of the time domain equation of a first order difference filter, and this is the transfer function. As you can see here that the zeros and poles of the transfer functions are at 1 and 0 respectively, and the phase and the magnitude response can be easily plotted, and you can see here that by the frequency response that this is a high pass filter which allows the high frequency components to pass. This is the pole and zero plot. The pole is situated at the origin and zero is situated at this circle. Now coming to the code, we are using the same input data. This baud rate is set to 9600. Now we are taking the array and initializing all the values to 0, which will be storing the output of the difference filter. Now this is the for loop which will run for 1000 times, which will be storing the difference value from the two consecutive input values, and when we plot it we can see that the blue plot is the input value and the red plot is the output of the first order difference filter, which kind of shows the high frequency components, the high slope components of the input signal. Now the third type of filter which we are going to study is the 3-point central difference filter. Now looking at the equation, the time domain equation, we can see now we are subtracting the previous to previous input from the current input to get the current output. The main difference between the first and second order low pass filter is that the stop band roll off will be twice the first order filters at 40 dB per decade. This is the transfer function which shows that the zeros are at 1 and -1 and the two poles are situated at the origin. The magnitude and the phase response can be easily calculated and plotted. Now we can see here by taking a look at the frequency domain response that this is a band pass filter, whereas the first order difference filter was a high pass filter. The two zeros are situated at the circle and the two poles are at the origin. Now in the code, with the same input data and the same baud rate, we have to just change the code from subtracting the previous to previous input data, and the output can be seen here as x as the input and y as the output value. Now we will study the combined implementation of both types of filters which we have studied, that is the smoothing of the first order difference filter output. So this is the input, this is the baud rate 9600, and now what we are going to do is we are going to pass the output of a first order difference filter from the moving average filter. The first order difference filter will help removing the low frequency components and will have only the high slope components. And after passing it from the moving average filter, we can remove the noise component from the high slope components so that we will be able to detect the peak of the signal very easily. Thank you.